PB. Well, it's a heavy metal, and so it's classified as one of the heavy metals, very heavy, and it's um, we know that it's soluble in water, and so we have them in water bodies as well. But this is a soft metal, malleable, and usually it has a low melting point, although it's heavy. And so normally we use that in mostly please Stephen, Ahena and Koma, can you mute your mic? Stephen, okay. So we get to hear or we got to see the use of lead mostly in the plumbing industry. So, well, most of the old houses were using, and we still have those pipes, especially when it comes to UCC here. I think in Crumer's time, so we still have those lead pipes still available in our labs and those stuff. So, but of course, gradually we are trying to replace those lead pipes. So when you come to UCC, when you go to the forest there, you see our pipelines, and most of them are lead pipes, the old pipes there. Well, we can also see lead being used in our paint and those. Of course, it was just because it was environmental friendly. However, we understand now that it's quite toxic, and so as we move on, we'll just get to see that. But then, because of its toxicity, we then decided to be using the lead balls in bullets. Okay, so that's something that came to replace the gunpowder. So extremely toxic that can cause what we call lead poisoning. Well, if you look at it, we can be using lead also in batteries as well. So lead batteries, like the secondary batteries which we use in our cars, we have those lead batteries as well. Well, once we begin exposing lead to air, we'll see that it begin changing color. So each bright color now becomes like a dim gray color because it has started corroding. So that's lead. The chief kind of or the common ore for lead is the ganila, which is that's the metallic lead. So, so please let me correct this. So it's not PS, it's PB. Let me correct it. Okay. So that's a ganila. That's the metallic lead. So what I'm showing here is a metallic lead. We should note that lead has two oxidation states, the +2 and then the +4. So +2 and +4. So it means that we can engage lead in various levels of reactions, which is the +2 levels and then the +4 levels as well. So we should note that. Now again, because it has the +2 forms, it can, of course, much reactive when it comes to, it's more reactive than iron. So it can poison our systems as well. But then we have lead when it reacts with oxygen to produce the oxides. Um, of course, the lead oxide can also, so this is a lead +2 and in the lead oxide. And that's when we add the carbide or the activated carbon to that, we can then be free to get the soluble lead. That's the liquid water, and then we release the lead, which can just be out. But again, we'll see that most compounds, the stable compounds that we have for lead compounds are the +2, which is the most stable, and then the +4. So we'll form more of the +2 compounds of lead than that of the +4. But then the +4 compounds can also exist. Again, we'll see that we use lead, especially like lead oxide in ceramics, in paint, and of course in the the shield, for example, in operating these radioactive species like the X-ray radiations, we can also use lead as a shield there. And just as I mentioned, we use lead in the lead batteries. So basically, that's what we kind of know. We use lead also for this. Of course, because it's quite soft, we use that in soldering, like on our motherboards and the pipes, and then the lead tapes, which we use, for example, when there's a leakage, we use this. I mean, the coal plus a lead tape, which we use in trying to um, seal those spots in the roofing sheets so that the leakages will stop. We know lead most at times in the use of bullet because of its lead poisoning and those stuff. So in effect, we can say that we'll see lead to be toxic, and of course we find lead in our fuel because we use lead as an anti knocking agent. So an anti-knocking agent in gasoline so that it prevents knocking, the noise that when the burning is happening in the engine, so it can prevent that. But then that becomes an organic lead. So the anti-knocking agent in gasoline is the ethyl tetraethyl lead. Of course, we should mention that organic lead is not just poisonous, but then it is extremely poisonous. So what it means is that once there is this incomplete combustion in these fuels that we are having, and of course, again, the fuel itself, if it has this anti-knocking agent in there, can also be poisonous to the system. And it's quite funny when, for example, you visit the mechanic shops and how they use these fuels a lot, especially when those that deals with oil, they use this fuel to be washing their hands and then a little bit soap and to wash that off. Some don't even use soap at all to wash those, but then after using the say the petrol or the gasoline, then you see them touching food and those kind of stuff. Of course, we say that we live in a country where grace abounds. So just by grace, we are still living. But then we should take note that ethyl lead is quite poisonous. So we should just know. So lead, we know that it's just poison the system, but we don't have any biological use for lead. Only that we know that the organic lead is extremely poisonous because it gets into the system and it begins accumulating, especially the plus two, the plus two or what you call the organic lead. For example, in the case of tetraethyl lead, it begins accumulating into the system, and gradually we'll see that it begin attacking the ion in the system by replacing the plus two ions, and so later the person becomes anemia, and that it accommodates itself in the cell, and then gradually we see it starts attacking the nervous system, and the person just goes off. So that is why we begin avoiding the use of lead. Of course, it was used in paint, but then later we realized that when you paint if, for example, if you have children in your home, definitely you see children licking walls and of course animals, and then they will be affected. Again, we also see some kind of levels of lead in, say, some drinks like whiskey, and of course, some smoking kind of like cigarette. Of course, for example, in tobacco, the amount of lead is quite high, and the tobacco industries themselves know. And of course, when you check the pack, they have even written the level there, and then they will write uh, smoking kills. It's not just a joke that they are just writing it. They are just warning you, and that sometimes we don't even pay attention to the terms and conditions unless we find ourselves in trouble. Then will go to the manufacturer, then it tells you, did you read the terms and conditions? If you take the person to court, you lose, because you should have, ignorance is not an excuse. You should have read the terms and conditions before patronizing in that product. And so you don't have any kind of cause to blame them, because they warn you that it's quite serious. Now, we'll see that when somebody becomes exposed to lead in the form of lead poisoning, the person will start experiencing anemia. Children, you see, it can affect the brain. But lead goes to target the nervous system or the central nervous system, thereby weakening your immune system. So it targets your kidney, and then it's quite difficult to, maneuver. Of course, we can treat such a, once we identify that that is lead, we bring in EDTA, that's a ethylene diamine, which is a good complexing agent for the plus two metals, calcium, magnesium, and then lead, so that we can just get the complex being formed. Or we just add a carbon to that, so that we reduce a little bit of vomiting in there, so that we can just get some out of it. So it's quite challenging when somebody becomes exposed to lead. And I must say that Africa has become a dumping site for this lead, because outside there they are trying to reduce the use of lead, but here we are. Once the matter, we can't create matter, we can't destroy matter, so they need to grow it somewhere, and that's where they begin throwing it to Africa, so that we will begin having access to this lead. And then if you poison yourself, you kill yourself, they don't really care that much. But well, the funny thing is that whatever the environment that they are trying to pollute is just an ecosystem. So they also get to have a feel of that. So as much as they want their countries to be clean and less polluted, they forget that once they are making here a dumping site, we will still carry that this pollution to them back, and that's a situation. So that is what lead can really cause. So you want to be very sure you don't get yourself exposed to this lead, so that you get contaminated. So that is it. The reaction which I know, or I just mentioned, is just the oxygen and then the carbon reaction that I mentioned. Well, the next one is bismuth. Bismuth, which is the Bi, very nice metal, which comes out with some different colors. Of course, we know bismuth to be a pentavalent. So it's, if you check the periodic table, that means that it will be under the nitrogen group. Okay, so it has 5 electrons at the valency. But then we know that, so bismuth, it resembles or have that family of the arsenic and those in that particular line. In the period group, see them with the family of those arsenic and those stuff. But that's a nice metal that we usually engage, especially for medicinal purposes, for cosmetic. And talk of these makeups that the women always want to be using to be deceiving the public, as if they look nice, but they are not, and they used to deceive the public. And that you can be getting a lot of bismuth with these different colors that they use in this cosmetics. Well, I say deception because I one time met one student during graduation. Now, in fact, I didn't even recognize her. So the lady was just staring at me, thinking that I should know that this is her. So I said, "Tune Kaimi." So, sorry. So I remember it was one of my students. Hey, and then they don't for power. God, that's the makeup have changed the whole kind of stuff. And I remember telling her that. So you see what bismuth can bring about. It can change your face so that you'll be deceiving us. So that's bismuth in those cosmetic industry. Well, in the medicinal industry, it's known to be pink medicine. I don't know if you've come across pink medicine for this stomach upset, diarrhea. When you have diarrhea, when you have stomach upset, antacid, go to the pharmacy, they give you this pink medicine, especially in kids. You see this pink medicine, which is the Pito Bismol. That's one medicine that they use, and this is just coming from bismuth that we use in medicine. Well, it's quite interesting that when we talk of bismuth in the environment, that it of course we mine it from the earth crust, but then it's quite much more than the gold that we have. Okay, so if you see the occurring how it occurs in the natural world or the earth crust, bismuth is above is twice times the abundance of gold. Okay, so we of course not in Ghana, but then in the total kind of minerals in the earth crust, we have two times. If you have gold like one, then bismuth is two times that of gold. So we have a lot of bismuth in the earth crust. Yes, and so we normally get to have a lot of deposits, particularly in US, Bavaria, Peru, Japan, Mexico, and Canada. They mine tons, heavy tons of bismuth, as we know them. But then we see that the uses basically is just for um, medication, it's for cosmetics, for painting because of its purple kind of color that it brings about. For safety systems, we can also be having bismuth also available that form. So that's just what. So hello, please, can you hear me?
No, we can hear you.
Hello.
Yeah.
Okay.
I
Okay.
hear you.
Sure. So
Yes, we can
that's
hear you.
bismuth. A minute. Somebody. Oh, okay. Yeah. So that's it. Well, the common ore will just be the sulfide bismuth that we know of. So Bi the Bi2S3, it will be the common ore for the bismuth mining. That's what we call the bismuth. Of course, the oxide form is the bismuth. So we can have bismuth engaging oxygen, which we call the bismuth. Okay, then we can have the bismuth or the well, that's a bismuth kind of form, the sulfide form. But then it can also engage acids. It can engage in the halite as well. So the bismuth chloride with water will form the um, chloride, bismuth chloride, and then the hydrochloric acid there. The bismuth, where's my casa? The bismuth and that of the acid produces, for example, if it is I mean the chloride, then becomes bismuth chloride. If it is nitrate, then it becomes bismuth nitrate. But then this is also an ore form of the bismuth, which we call the bismuth. We should note that bismuth also has the oxidation state of +3 and then +5. When it comes to the oxidation form, we don't have any unique kind of pattern where the elements must follow, apart from those in the main group. That's a group one, the group one, group two, and then the group three, which is the aluminium. That will have a fixed oxidation state, which you know is +3. But then transition element or the post-transition element are variable. They are not kind of fixed that once you are in this group, if you have this oxidation number, they vary based on each element. So we can't just restrict. So basement has this unique trans oxidation state, which is the +3, and then the +5 as well. So sometimes we say it's a pentavalent. So that's the basement for us. Well, let's round it up with so that's the main group metals that we have. But then, so talking of metals, we can also consider some common or most important metals in the transition metals. For example, copper, silver, and gold, which we call them the conjugate metals. So for making coins, conjugate metals. So at least we know it has evolved from the bronze to the brass. That's copper at play there. So that's a conjugate metals, and it happens that these conjugate metals are quite expensive. Copper and silver and then gold are quite expensive. So we look at those conjugate metal. Later, we will then consider the poisonous metals here, which is the last group in the transition metal. We will not consider the rest of that. So let's look at those conjugate metals. So for example, copper. Okay, so copper, very soft, malleable, and most of our cables that we have are copper cables, like the electrical cables. So copper, if you look at it, the atomic symbol is Cu, meaning it has an old name. Well, if you check the periodic table, we have about 11 elements on the periodic table, which have their symbols from their old name. So 11 of them. Then copper is one of them. So we should take note. Well, meaning the old name for copper is coprum, which is the Latin word for, bright. And that is where we have copper, Cu. Okay, so as I mentioned, in most of our electrical kind of appliances or the cables, we have copper there because it's a good conductor, both electrical or thermal. It's a good conductor of heat and then electricity. So we use copper a lot. Now, if you look at it, where we have a lot of copper deposits is in Zambia. So Zambia mines a lot of copper from their country. However, those mining companies belongs to the Chinese. It's not for Zambia as a country. So the Chinese are having or citing their companies there. Of course, they have bought it outrightly. So the country has no share in the copper mining that they mined in there. So we have a large deposit. If in Africa, we have that deposit in Zambia, but then they don't have that share that much. Like we have oil in our country, but we don't have that much. I mean, percentage wise, it's only 10% that we are having. We have lithium, which we are just going to be giving away 95 against 5. So that's how the whole thing is. But of course, there are some countries which are even having higher deposits outside, but I don't know why they are interested in Africa a lot. So, for example, Chile. Chile is the highest deposition of copper, followed by Peru, and China itself is also having deposit. The US also has that. Of course, some deposit in Russia and other countries put together. We have copper, but copper has been evolving over the years. In history, we see the Bronze Age, which is the alloy bronze making headway. That's it was called a reddish gold, reddish gold. So that's what will make way or make history in some at some point in life. And so they were using it apart from cables for coins and alongside silver and gold. They were just having that. So, for example, if there's a medal, you see we have bronze, we have silver, and then we have gold. So the highest is the gold then the silver, and then the bronze. So it means that in categories of, expensive metals, and you can't count copper out. And that we have those coins there. Now, if you look at it, I think US is still using those copper coins. So they are cents, so copper made coins. So those bronze copper. So that's why I showed you the man who always wants the best for his country, US, now targeting Greenland. Is now targeting Green. I'm sure you have read that there may be a division in the NATO. So NATO now is going to maybe fighting their own member, which is America, because the NATO countries, which is the European countries, coming together backed by US. And US now is against one of the country, green country, which falls under Denmark. So they may fight US very soon, whilst he's also preparing against Russia. That's the man. So he's still looking for a lot of
In China.
minerals and yes, and Greenland has those a lot of minerals. Well, he's hiding behind security, saying that Greenland is a country or a land where it's more secure. He can just be seeing Russia's attack and those kind of. But we know that experts knows that that is not the aim. That's what he does. He did when they went to Iraq and those this. It's just because a mineral is there, he wants to take advantage of that. And now there's this talk that NATO will not agree for him to take Europe. So let's hope. Already China, and then China, which wants to take Taiwan, supported by Russia, and Russia wants to take Ukraine. China now is an alliance, and so it's going to be so funny how US can maneuver if he wants to take Greenland. But it is said that Donald Trump, once he says something, means that he's going to do it, and exactly what he did to is it Venezuela, where he has
Yes.
captured the president. So we are hoping to see, but then it's just because of the minerals which is available in that, especially the rich minerals which Greenland is having. Well, so we have made that history, and they're still using copper as well. Well, if you take, for example, copper sulfate is one of the it's found in those agrochemicals which they use in trying to um, more or less like the weedicides, the herbicides, and those stuff in treating or killing those weeds and those stuff. So that's copper sulfate in there. Well, um, again, we'll see some copper compounds like the ferrin solution, which is used in testing sugar, the various six-member sugar, glucose, fructose, those mannose, and those are that's ferrin solution that we use in testing whether there's presence of sugar or not. Well, we will say that copper is a trace essential element to us. Trace essential. Again, please note my words. Trace. We don't need that much. Just a trace amount. Just a trace amount, because some enzymes are copper related enzymes, which helps us in the energy transfers, the ATP synthesis, and those are. However, excess of copper can be toxic to the system, can be poisonous to the system. Now, when we have excess of this copper, it creates diseases like the Wilson disease or the Parkinson disease, which can destroy the bones and then also cause mental illness as well as affecting, of course, because copper is +2, definitely your iron. So all those metals that are, it's rather unfortunate, iron is not quite reactive. So if there's any metal that is reactive more than iron, it's want to do the displacement, and that is where we begin getting affected in that. So The Wilkinson disease affects the brain. Of course, in children, you see them having soft bones, and of course, hair loss and those stuff. In adults, we'll see that it can affect your central nervous systems. It can affect your liver, your bones, causing arthritis, and of course, the heart and eye can also be affected. And that is the Wilson disease. It's a generic disorder when there's excess of copper build in the body. When there's excess of copper build in the body, you see that the liver begin having problems with that. And so you kind of experience vomiting, weaknesses, fluid building up in the abdomen, and then also in the legs, so that the legs begin swelling and those kind of stuff. Again, you will see that you'll be having itching skins, and then if you are fair, you have a yellow, especially those whites, you have this yellow skin as well. And this is a Wilson disease. It's quite kind of can make, especially the elderly. It's because, of course, when you are growing, your immune system also becomes weakened, so it can really break down your immune system as well. In terms of usage, we see copper because of its electrical properties and heat. We see building, see these electronics, electricals, transportations, and those machineries, and of course other consumables. We see the use of copper also there. Now, copper, we have the copper one and then the copper two as well. So that's the oxidation forms of copper. The next metal is silver. Okay, so silver very soft, white is kind of in color. Okay, so as I mentioned, you can just guess. So next to gold, after gold, very expensive metal, but it also has this electrical and thermal conductivity properties as well. That it kind of has optical properties. And so it's the silver bromide, for example, is used in this lens. Now, I think because of digital cameras, we don't normally use this, but then silver bromide was used in this lens photographic. So that's for the what we are calling flash. So you take a picture, you hear boom, then sometimes when the picture comes, your eye even becomes red. That's the photographic kind of light that we are seeing coming from that silver bromide. Okay, so we use that in lens. Now talk of stainless steel, we have silver components in those stainless steel. Of course, now lens not in just um, the flash, but then in the photochromic lenses, we have silver there because silver absorbs light. It darkens when the light is so bright. So when like the rays around you is so bright, then the lens will give you a nice kind of light spectrum so that your image can be captured so easily from there as well. So that's silver. So basically, if you look at it, we'll see silver in electronics, in coins and medals, photographies, the jewelries, which of course silver jewelries are quite expensive and next to gold as well. So you see those that are there. And this is white, it's normally called a white metal, very white in that in color. So unique and those stuff. Now I think now we no more use this silver related film. So this is a silver related film, which those the Indomie children would not meet this. I'm very sure, but then I don't think it's quite old where this one is a point. Do you see my pointer?
Yes, sir.
Please, guys.
Yes,
Yeah.
sir.
So I think this was what we were calling. So the images are formed on these ones, then you take it to a dark room where you now generate your image. But of course, now because of these printers and color printers, now we don't develop images from these films again. Just take the picture, print it out, and that is why. So this will do, but this is the silver film. We'll use silver to just create this particular, and it absorbs the light around the person. So you, the person, becomes a dark image. So the light around it is an image which is formed on that, so that you can develop that, and then you get to have the clear image as well. Now, the next metal is gold, very bright yellowish metal, and of course, one of the expensive. Well, it also has an old name, the iron. That's why gold has an atomic symbol of AU, iron. Very the old name um, that it's quite pure, but we don't find gold in its pure forms unless it has been refined over and over and over. Now, we can find gold on as part of our electronic system, for example, in computers, what we're calling the memory chips. We have some small deposits of the gold which they were using as part of the semiconductors. So gold is there, so you can extract gold from that as well. Well, because gold is quite expensive, I think at a point where some people were trying to replace some of their teeth with the gold. And when I get here, I tend to ask the Muslim friends what that means when they visit Mecca, and then some can. Of course, I was told that it's not compulsory, that at least, especially the women, the Hajis, and then the Alajis, when they come with the gold teeth. And what that means. Of course, gold is not reactive when it comes to the body, and we have traces of gold in our system as well. So our body has traces of gold. So the allergy, and that's why I got to understand that allergy basically means a stranger. So you visit Mecca, you become a stranger. So you come from there, you are a stranger in that pilgrim land. So some, when they are leaving, because they want to show that they have visited that land before, they just buy that gold and then use that as a sign of you being there. So if you talk of gold, we can see a lot of people buying gold bars and gold coins, and that's what makes some countries rich. I say some country, not Ghana. We have a lot of gold, and it's so even funny that we can even sell gold and run at a loss. And this is only found in Ghana. As expensive as gold can be, gold board could sell gold and become, and then we run at a loss. And that's just so fun. That's our country which we live in. And that we see that in the dental world, of course, I mentioned for use as jewels, electronics. So some coins are, of course, but then people buy that because in the medicinal world we are using gold. Of course, research is still even going on in the use of gold-related drugs. So, because gold is somehow inlet, means that once it forms a compound, it can really well. So the dentists or the dentries are still using gold to replace some teeth, and that countries that are rich are using gold. So when it goes to the Arab world, that's where you see the real use of gold. And their gold kind of plated chairs are gold plated. I saw one video where it's even the WC is made of gold. So you can see that we are extremely kind of rich. So we have these gold for those jewelries, rings, and those stuff, the coins that we have, the dental or the dentries still using gold. And of course, the medals that we are using that gold. It is said that some of the space ships or the satellites have some component of gold also there. But I mean, when you visit those Arab countries, you see the real use of gold. Of course, they mine the gold and they buy gold as well. And so it is just, and a country is measured by its worth by the either the amount of gold that you have. So in the World Bank, you deposit gold, they give you permission to print your money. And that's what Ghana is trying to do, to get the permission to print our own currency instead of taking gold to deposit before to get the permission to print. So if we can pass a law to print our own currency, then can stabilize our economy. But I think we're still talking about it if that is going to be possible. We claim to be a sovereign country, yet we are not that sovereign as we we want to. And then other countries, when they go for bankruptcy within some few minutes they revive. I mean, COVID hit US so much that it nearly touched 500 years deposit of oil, which of course at that time Donald Trump was there. He was warned not to do that. Immediately COVID was reduced. He just pumped in dollar. Nobody stopped him. He pumped in dollar, and US was back to his feet again. And even warned the World Bank if they are trying that, he's going to sanction them. So that is our word for us. But then we use gold a lot, and that it beautifies those stuff. Now we see gold as used in treating, say, arthritis, very kind of useful. But of course, the research is not complete. Where, as I mentioned, we've seen that much of gold-related drugs are quite effective. So we are still looking at how can be using those gold-related kind of stuff. Now we'll see some gold coated. Now the purity of gold is kind of something that will bring the name. So if we have, of course, we can't get to even 100% pure gold. And so we have like 24%, 50 something percent. So there you see the 24 karat gold, meaning impurity in there is almost like 24 as we proceed to there. But then as we refine, we can be getting more kind of so gold comes with other kind of combinations as well. It's not like just pure gold, but then we get it with other metals combined. So we kind of use other means to separate the gold from there. When we get to mercury, we'll see either to use mercury or cyanide to separate the other kind of metals. But that's how we mine that. And it's unfortunate that our system here, we have found a use of those mercury trying to mine our gold, but then people are still having access to those chemicals in mining as well. But then you can't get to see. So the first time I kind of, well, I was supposed to go there, I nearly said that this is not true. It's not. I thought that gold was shine. It should be shining like, for example, like this ring or those coins. But then it's not that shining if it has not been refined so often. So we should get to know that. Okay, so that's the conjugate metals. We want to look at the rest and try to investigate a little bit more, especially those the so-called poisonous metals. Well, not all of them are poisonous, like zinc is not, but then the heavy metals like cadmium and mercury are. So we will just narrow it down to just zinc, cadmium,
And I
and
say,
mercury. Yes, sir.
the zinc, cadmium, and the mercury, are they also part of the coinage metals?
No. So the conjugate metals basically is the copper, silver, and gold.
Silver and gold. Okay.
Yes. Uh, but then because these are also common metals which we engage the mercury, cadmium, for example, in our case, the water pollution. And of course, zinc is also used. It has a potent biological use, and so it's quite common. That's why I want us, but that is not conjugate metals.
Yeah.
Okay. So we are looking at zinc, cadmium, and then mercury. So I'll just take them one after the other. Of course, they are all metals, which has the properties of these metals, but then they belong to the transition metals. So if I take, well, I'll take the zinc and the cadmium alongside because I mean, their size is quite close, although one follows the other, but the size difference is not that much. So if you look at the common ore for zinc, we'll see it in the form of the zinc sulfide, which is the spatierite or the what you call the zinc blender. That is on some rock. If you check the shape, this is how it looks like. So we have the zinc blender, of course, the zinc sulfide, that's a common ore. And when exposed to oxygen, it forms a zinc oxide, and then we add the carbon to that or the charcoal to it, then we'll free the zinc metal. So we then get to have the zinc metal floating, and this is a flotation process, flotation method. Maybe I should write it and then so I'll just so that's the steps that I'm showing here. Sorry, I think my distance is off. Okay, so that's the um, flotation method or process, if I should just. Yeah, so this is where we have the blender, the zinc. When we say zinc blender, it's just the zinc sulfide. That's what we call zinc blender. Okay, so when we have that, we expose it to oxygen. That will form. Sorry, where's PowerPoint? Yeah, so that will form the zinc oxide. So once we add carbon to it, we'll then be releasing the what we call the zinc metal. That so it goes through steps like the flotation. Then the next step will be when we are adding the oxygen in there, we will call it the roasting. Then we'll then add the carbon in the form of reduction, and that is where we release the zinc metal. Okay, of course we can purify it more. We'll try to purify it more once we have other metals going alongside with the zinc, like lead and those stuff. So we'll try to do fractional distillation to separate the two metals. So the lead will be kind of separated from the zinc for just purification kind of processes. So that's just the purification method. Of course, the extraction of the zinc is quite an old system. I don't think if we'll still have. So the picture which I'm showing here is one of the old industries which they used to extract lead and zinc from the sulfide, the lead, a zinc blender, one of the old cited in Europe. But then I don't think if this still exists, but then I took that picture from that system. Well, we can also have the cadmium sulfide, the yellowish cadmium sulfide, which is this, sorry, powder kind of stuff. So we extract it also, and then we can just get the sulfide of that as well. But the extraction is just very simple. Once we have either the cadmium sulfide, which is just this so-called smoke dust, what we just need to do is just add an acid to it or add it to an acid, and then we'll filter this residue. that the fractions is what is going to separate between the cadmium and then the zinc. But we should note that well, cadmium again is the plus we can have the one and then the two as well, but then the plus two is quite similar. So they have similar properties. Both are, of course, metal or the aqueous metal as well. Sorry. Sorry, sorry. Okay, so that's just that. Now, in terms of usage, we can see zinc used in brass, and of course as um, a metal which also prevent corrosion, and so it's used in protecting iron, the galvanizing of ions, so that it doesn't rust. We'll see that zinc plus barium sulfate gives some white pigment in paint, which of course it's if there's lead in the paint, this try to protect the lead so that it doesn't expose the lead so that it becomes poisonous. So that's, but then if you look at it, the most usage of zinc is what we use in this galvanizing of um, metals. But then in human systems, we use zinc because that is also a trace metal. But then it's quite essential because our DNAs, enzymes, so we have those enzymes that are zinc related. Okay. However, again, the extreme storage of zinc can cause diarrhea, headache, and abdomen, but that is not that poisonous as it can be. But then it can also threaten life. Not that poison, but then it can threaten life when there's an overdose of zinc. Though we need it, but then we need that in trace amount. Well, science, when you begin seeing that you have been exposed to excess zinc, is when you have nausea, we have vomiting, stomach pain, diarrhea, and that you kind of see that we have excess. When of course when we check the zinc, copper index deficiency, it can be life threatening as well. But we need zinc to boost our immune system. I think during the COVID, one of the medicine that they were using to boost immune system was a zinc supplement. So they realized that the iron supplement was not really kind of effective. So they give you the zinc supplement, which also really boosts the immune system so quickly. So that's some pills that were given to those patients to recover so quick. So that's a zinc related. Um, I mean, medicine that we use. But we know the compounds of zinc. We get to use them paint, and then of course some treatment of water, and then some skin diseases we can also use zinc. For example, the zinc oxide. And how do we prepare this zinc oxide? Once I have a zinc metal, expose that to oxygen, we form the impure zinc, which we can refine it more. So once I can just add like an acid to that, refine it so that I can get my pure zinc. Or when I have a zinc nitrate, I can also get to have my zinc oxide or the carbonate. I can have my zinc oxide as well, which I said we can be using for example, skin treatment as well. So that's I think I've mentioned the common stuff. But for cadmium, we don't really eat cadmium, and cadmium is one of the poisonous metals that we have, and it causes this cadmium poisoning. The first case was diagnosed in Japan, so they call that disease the Ita disease. That is the it disease, which can soften the bones, and then causes this osteoarthritis, and then of course, if you look at it, and bend that. So it's quite poisonous to our system, and we know the mechanisms that goes in that. It affects your respiratory systems, your reproductive systems, your skeletal systems. You can also get to, and then the kidney as well. So that's the lead. But we are still using lead in the batteries, lead batteries, or the nickel cadmium batteries. Okay, so we are still having these types of batteries available. Again, we have high deposit of cadmium in tobacco, which is also part of the reason why they write that smoking kills. So that we have that in tobacco as well. Now, talk of these ties that the car ties is that component of the zinc oxide in those car ties. So where they bend the ties, exposes or releases cadmium into the atmosphere. So especially those that want to be using ties to be treating their cows, or when they kill cows and goats, then you see them burning ties. So that's meat. You should be very careful about that, because there is the release of this cadmium oxide, which can also create a problem to your system. Okay, then the electroplating systems, or the discharging waste, there's this cadmium also in that. That's where our water bodies now we still have cadmium, which has become one of the headache for Ghana water now. How we can be getting rid of some of these heavy metals. Of course, some of them we can, but some we can just reduce the content in that. We can't really get rid of all the in the heavy metals completely from our water bodies. But I think the government is bent on that, trying to see how you can deal with the exposure by now. And so, because if not, we all die. Because gradually, and those communities which has really been impacted can just see the impact on their life. And it's just getting to the cities as well, because there are foods that they bring for us to buy and then eat are all contaminated with these heavy metals. Well, we'll talk of mercury, the so-called soft metal. It's not the only metal that is liquid at room temperature, but then some metals is maybe above some room temperature, 25 to 30 degrees. You see some metals also melting. That it happens at just as 24, 25 degrees. You see metal. What it means is that below 24, mercury is hard. So please note that mercury is hard, and that's how they mine that. We get to have mercury a lot from the volcano, of course, in the earth crust,
Hello.
but then coming from volcanoes. Yes, sir.
So the bromine, is it also liquid at room temperature?
Bromine.
Yeah.
Yes. So we have chlorine as a gas, bromine as a liquid, iodine as a solid.
Oh, okay.
We'll come to the non-metals to see that. Okay. So the most common ore for mercury is cinnabar, which is the reddish kind of. So this is how originally mercury looks like. These nice crystals that we see in the rocks. So that's this mercury. So cinnabar, that's mercury sulfide. That's the original form of mercury in its ore form. And that's how we mined the mercury. So we mine mercury in the cinnabar form, the reddish crystals that we see. And then we extract it by flotation and then by roasting. So by flotation meaning we add to oxygen and then we add carbon to that to just release the mercury as we have. Now we should note that, of course, initially we didn't know that much about mercury. And so we were just using mercury in most of our reactions, and then industries using that. In fact, in the medical field, they were using mercury in treatment. And then in our thermometers, you see, I think the old thermometers still have mercury, but the WHO has banned the use of mercury completely. So hospitals that are still using the old thermometers are quite breaking those rules. So the because once it breaks, it hits that and breaks. Mercury is volatile. So that liquid, that shiny liquid that you see on the floor is not actually a complete mercury. Some has evaporated and then form organic mercury, and it's getting into the system. We heard of this mercury poisoning in Japan, what you call the Minamata case, where it nearly wiped a whole community in Japan called the Minamata community. It wiped everybody. So it started from an industry releasing mercury into the water. So the fish were contaminated. Then the people started fishing in the river, and then the people also started dying from the mercury poisoning. That's the Minamata case. I don't know if you have heard about it. It killed almost, it happened in 1956, killed almost a community. And that's the organic mercury, the metal mercury, which was released from the factory into the river body. That is something which later then drew the people's attention that we should be looking at it. So I think they said that during that time, so victims almost people who were affected like were 2,200, but out of that 1,784 died, and then the rest were kind of survived. Yeah, so this mercury poisoning is quite dangerous, and that's where we come in. We are saying that it's dangerous, but we are still mining with mercury. So foods which are consumed which contains mercury will just be poison, and so the poison continues. So it really affects children and unborn kind of because of course their immune system are not that strong enough and they are vulnerable, and so the mercury can easily affect them, and then it becomes a potential threat to them. So it should be, yes.
The purchase of these chemicals, don't you have rules and regulation for it?
And that's what I mentioned, that standard board should be regulating any product that comes into Ghana from our ports and then our harbors. But then you can just agree with me how we are interested in money more than life. So the people are so importing these chemicals into the system. And how they do that, we can't tell unless we have a robust way of controlling. And they come in heavy tons, heavy amounts through our harbors, and nobody can stop that. And we are still regulated. You go to the marketplaces, if you want something to buy, they will sell it. So I think last year or last 2 years, we had a conference where the Ghana Chemical Society wanted government to even give us that so that we can regulate, because we were even coming from the angle where this fire outbreak in the market, fire outbreak there. We later realized that some of them are coming from these sales of chemicals, like somebody selling sulfuric acid. How can
Yeah,
somebody be who is not a chemist selling sulfuric acid? And
yes,
you can clearly see there are a lot of chemicals, like for say these chemicals that they use in making these liquid soaps and those stuff. They are
yeah,
there in the market, very common. Who, where did they get it from? Who gave them that permission to? But then they are common there. You can just go to the market and buy those chemicals and come and do your liquid soap yourself, and parazoles and those
yeah.
things. And so I don't know. We love in our country. We love money more than life. Uh, if not, why would we allow that to be? And so mercury is abundant in our system here, very abundant, and that's where some like those raising the argument that this say we can't stop it because there's somebody's business to be selling mercury. So how would you be stopping that business? So if you agree, and then I agree that I'm not selling those chemicals, of course I'll lose because I'll lose money. But then if I think that life is more important than money, I'll stop it. And so nobody will get mercury to buy. And if they don't get the mercury to buy, how are they going to mine in the gold? So that's just something that we all must decide to buy that. But then we'll see that we use mercury, for example, in our case, to be, I mean, binding. It's a good binder, and of course, it also releases other metals, dissolved metals like gold, like silver, like copper. So once these metals are binded to other kind of metals, once you drop mercury there, mercury will break those bonds that these metals are having, and then will form the bond instead, and then we'll release the copper, the gold, and then the silver. That's where we use this mercury in this the kind of mining. However, mercury is quite, I mean, tricky. It has a oxidation state of +1, +half. Okay, so it changes and it goes in pair. So it's Mg2, 2 plus. So it goes in pairs. And quickly you can see that it can just restore or just take over where iron is available. And so it's just quite well, it engages other kind of reaction, especially we use mercury in converting ketones to the straight chain alkane, which is the clemensin reduction. So zinc in mercury instead of hydrochloric acid, clemensin reduction, which organic synthesis we uses that a lot so that we convert or we reduce ketones to alkane. That's a nice reduction, but this must be done under a control system so that we don't get to expose the mercury which we're having. But we see that we have mercury in thermometers, in the measuring of pressures, the barometers, we see mercury also helping us in doing those measurements as well. But as I said, we didn't know that it was poisonous. So at first they were even using, the dentist was using it that refilling teeth, the holes that are in the teeth so that it can just done. But we've seen that that's where we are trying to, I mean, if possible, get rid of this. But we still have them in the system. We still have the batteries, the mercury batteries also there. And I think, well, it has not been old where we replace all mercury bulbs. Those yellow bulbs, I don't know if were replaced. I mean, the tungsten bulbs were replaced by mercury bulbs. But now we have also begin replacing these mercury bulbs with the LEDs. So I'm sure you've seen these mercury bulbs.
Yeah.
Uh, yeah, of course, they said that it's high. It has high consumption. So we just when we're replacing the tungsten, that's yellow bulb. Of course, when you go outside the cold countries, they still use the tungsten bulb, the yellow bulb. Of course, it's just psychology. Yellow creates heat, and so in our rooms, those times the yellow bulbs were very hot. It makes the room very, very hot. So people resorted in rather buying blue bulbs instead of those tungsten orange bulbs. And then later they say, okay, then the white bulbs. Of course, white means it's cold. So the white will make your room cold. But if you have ever touched these bulbs before, you see how it is generating heat more
Yeah.
than this. So it's just psychology. But then later they say, okay, the mercury is just creating or just having consuming much energy. So they replace that with the LED bulbs. Which, but I think still, we people still sell the mercury bulbs. They are still there in some shops. These mercury bulbs are still in some shops. So we'll still use that. So what we need to be careful is this poisonous metals, lead, cadmium, mercury, and then arsenic. Okay, so arsenic also in the non-metal, but then these are quite a problem to us. Of course, I think water and sewage has a way of removing arsenic, but that's extremely poisonous. Now their problem is these mercury and this cadmium. Lead, once they can, I mean, the water is far from where the lead is exposed to the water bodies. There we'll see that they can control lead. But it's quite unfortunate that these systems are still ongoing there. Yes, yes. So
So, when you go to the fishing communities, I think for the lead, most of them are using the lead attached to the net. I don't know whether
yes,
we have a particular effect as they are using it at the coastal area.
yeah. That. Thank you. So that is even nice. I forgot to even mention that. You see, again, we are still not safe. You see, the government is trying its possible best to see how we can regulate this poison that we are engaging. And so, if you are aware, we can't export our fish outside Ghana. It can't go to, say, Europe. They are even place us on a red kind of line and red flag kind of countries. So we can't export our fish just because of some of these poison. So at the point, some fisher folks were using dynamite. Some of them now what has come is to use poison, which they have warned them. So they are poisoning the fish. And it's so funny that some, apart from the fishermen poisoning them in the water and bringing them out, those that are selling, some of them are using formalin to store the fish. Some of them, like I don't want to mention any fish so that it will be frightening. But then this, or in the discussion of why the government have to close this seas and those stuff, this discussion came up. So those that are in the market selling the fish are quite, now it's even surprising the smoke fish, they are using this oil to make it loose, and that is not a vegetable oil, and these are poisonous stuff where they are making their smoke fish look new and fresh. But
Yeah.
then these are all kind of, so we are killing ourselves just because of money. And the most threatening one was the one that I saw when it came to vegetables. So there, I don't want to mention the chemical name because I'm a chemist. I don't want to put in pressure. I mean, frightening people. But then once you remove a plant from the soil, that plant must wither. Now you go to the market, you see this vegetable so fresh, not knowing they are mixing this chemical, and then they'll sprinkle on it so that it revives the chlorophyll, and then that's a magnesium puffin. It revives it and makes it look fresh. So when you don't buy it, they'll take it home, come again, sprinkle it, and then it looks new. Okay, these are all chemicals which we are just buying and injecting into our system. And I think when it comes to exporting, Ghana have been placed on red flag. And the way we use chemicals in handling food is one of our dangerous kind of, and that's why our life expectancy, if you're aware, is reducing and reducing and reducing just because of how we are using these chemicals. Yes.
Sir, is it these days we have been taking tilapia and this chichinga from the Abuchi people, and what they use in roasting those materials, the metal that they are using is the condenser of the fridge.
Yes. Yes.
Those metals that they use in roasting the
Actually,
tilapia and the chichinga, does it have any particular defect or not? Because they will be using them and be using brush at the same time. I don't know. It just came to my mind
they
to
are
ask.
even using not a cooking oil. Some of them don't even use cooking oil. I don't know where they buy the oil from, but then, and we have seen some research publishing that we have this PH8, that's a polyaromatic in that, and these are cancer causing agents. But of course, again, what can we say? We are living in a country of grace, where we are surrounded by poison, but then we survive by grace, and so their actions and acts are just something that we should be considering. At least an advice somebody gave me is that when you don't know the source of the food, don't eat it. It doesn't matter how attractive that can be, don't eat it because you don't know what has gone through. Now, the red oil that we sell in the market coming purely from chemicals, not even at first they were adding chemicals to it to make it red. Now this is purely chemicals. So we are now having synthetic oils, and so note that our system is organic, it's purely organic system. So any synthetic form is going to be against the system. So and those I mean they are making their money. Of course we live by grace, so you can just if your grace is high, go and patronize that. But if your grace is very low, we all die, but at least some of the death we can reduce the kind of intake. So please let's try to use that. And it's quite interesting how people are making money irrespective of how they make their money. They don't care. So you go to these shop bars and those restaurants. It's quite an expensive restaurant, but then there was one restaurant on campus. They call it campus family canteen. It was very booming. Those times, we didn't even know what restaurant was. So when you get in there, they serve in plates, and then it's quite expensive. All of a sudden, it just went down just like that, all because a student went to find out where they cook the food from. Then they will bring it to campus to that restaurant and be selling it. Here, Gota, and how they are doing their things. The student came to break the news, and the restaurant just went up just like that. Okay, so we should be very careful. If you don't know where the food is coming from, who is preparing the food, at least control yourself. You will not die. If possible, prepare it yourself. If you can do it. If you don't have time and you are going to be buying, buy it from people you know. Okay, thank you. Let's move on. Okay, now I want to now look at the other part of it, the non-metals and then the metalloids. Okay, so I'll come at a point to come across the cyanide and the mercury, so the gold mining. I'll just see how we do that extraction from the non-metal perspective. Okay, so if I look at the periodic table, those elements that can easily release electrons, we call them metals. Those that can accept electrons, we call them the non-metals, and those that falls in between that, call them the semi-metals or the metalloids. So the metalloids are the boron, the silicon, the germanium, arsenic, then the antimony, xenon, and then polo. These are the metalloids. Now, so we can list some examples of these non-metals and then the metalloids. So if I'm comparing the two, like metals and then the non-metals, we'll see that the non-metals forms anions, whilst the metals will be be forming. So opposite the properties of metals, it will be the non-metals. So if I take the main group element, this part in the P block, so I've treated the metals here, the group 3 metal, which is the aluminum, and then the post-transition metals. Now we can look at those that are, apart from these metals, are the non-metals. Then we have this zigzag line, which will be classified as the metalloids, the semi-metals. So let's take the non-metals and then also, just as we did for the metals, have their general properties, then take the group and then we'll break them down by taking the element as one after the other. Well, the general form, we'll see that most of these non-metals exist as gases at room temperature, not all. We have exceptions. So we have like boron, that if you are getting down the group, see that they changes from gases to become liquids and also to become solids. But then we'll see again that the non-metals will be poor conductors of electricities and of course heat. However, when they get into contact with say metals, they may kind of be allowing flow of, but if it is purely non-metal, so the bonding system, have non-metals combining with metals to form ionic, the non-metals themselves engaging themselves non-metals, that is a molecular compound, so that is just neutral, so that's a covalent system. Then of course the semiconductors can also be there, and these semiconductors are the metalloids, combining these metalloids to form the semiconductors, and these are a non-metal. The first member of the non-metal which we can treat is hydrogen. So let's say, so remember that we said that hydrogen, sometimes we put hydrogen in group 1, but then it is not a metal. It is a non-metal which exists as H2, as the hydrogen gas. So that's the first member that we can be looking at. So sometimes we can put it here as a group 1, sometimes we can put it here, the group 7, or we can just put it in the middle. So that's the hydrogen that now if you look at hydrogen, it's quite the most abundant chemical in the universe. I mean, in the earth crust, in the atmosphere, we have hydrogen playing a major kind of in its form. So its occurrence will be most abundant. After it follows oxygen and then silicon in the earth crust. Yes.
Sorry, the hydrogen and carbon, which one is more abundant?
In the universe, then hydrogen is most abundant.
I see.
Okay. Well, carbon will come to carbon compounds. Carbon is not that. So hydrogen is after oxygen, it's after silicon. Like in the earth crust, we have more silicon, we have oxygen, then hydrogen, than we have carbon related. Okay. So we'll see that hydrogen occurs in the form of water in their all forms. We'll see it occurs in the form of water. It can combine with carbon and to form the organic, so what we call organic compounds, like the hydrocarbons, the other kind of functional that we can talk of. That's hydrogen. While we should also note that in the atmosphere we have hydrogen existing in the atmosphere as well. So yes, let's note that. Now, hydrogen can exist as or can have these. So that's the third most abundant in the earth crust, following oxygen and then the silicon. And then hydrogen has three isotopes. Isotopes are elements of the same electrons or protons but different neutrons. So that makes it having different mass numbers. So they exist in different three different isotopes. We have the proton, we have the deuterium, then the tritium as well. Now the tritium is quite radioactive. The deuterium is heavy, and then the lighter hydrogen is the proton. So what it means is that if you are forming compounds, whatever H2 can form, we can have D forming that, we can have T forming, we can have probability of even missing them. Is that okay? But then the T is radioactive, and then the D is heavy. So for example, if hydrogen uh, forms compound with oxygen, which we call water, then the heavy water will be the D2O, not the H2O. So the H2O can be in different forms. We can can have the H2O which has ion in them. And of course, depending on the type of ion or the ion there, we can have what you call the hard water or the soft water. And of course, we can have the deionized water, or if we have distilled it from other impurities, we call it the distilled water. Now, the D2O is called the heavy water, or what we call pure water. And so the sachet water, which we are calling pure water, is not pure water. That's just H2O. I don't know where they got the name pure water and what makes it pure. I think maybe it's just relatively comparing to the treatment of tap water. So they call it pure water. But that water you are drinking is not what you call pure water. The pure water is D2O, not H2O. And the D2O is also known as heavy water. Of course, it's carcinogenic. We don't drink that water, but that is what you call pure water. So you look at the various isotopes
Tell us
and
that.
then, yes, sir.
What makes D2 heavy metals? The deuterium. Or what makes it heavy?
Well, you look at the mass.
Okay.
So the mass of the proton is 1. The mass of the deuterium is 2. Well, at the mass numbers, not just the mass. Of course, if you look at their masses, they are just going to be, you say that the deuterium is supposed to be heavy. But then that is radioactive, so we don't engage that. So it's only the deuterium and then the plutonium that we engage. So that's why this one is heavier than this one.
Yeah.
Okay. The deuterium, tritium, we don't engage because it's quite radioactive. It's an radioactive isotope. So its abundance is not, is quite limited. So you can see it's even less than 1 in 17,000 atoms, very, very low in terms of natural abundance. In terms of deuterium, that's almost like 0.2%. Now, the most abundant one is the plutonium, which is 99.98% or 99%. That's the most common one. That's the plutonium, or what you call proton. That's the most. So the water that you are drinking is the one that is coming from the H2O, not the D2O. So the D2O is what you are calling the heavy water. In other words, pure water that cannot engage any other element. So that is pure. The H2O can engage other um, metals or other kind of elements. So that can be an impure um, element. Well, we know that hydrogen can lose electron, hydrogen can gain electron, so it can become +1, and then can also become the -1. So we call it the hydride, then the proton. So when it forms compounds, it can be the positive compound, or it can be, the positive ion, or it can also be the negative ion. So basically, we'll say that in terms of bonding, we'll see that hydrogen can lose its valency and become +1, or it can acquire an electron and becomes -1. That makes it looks like the halogen. Okay. And then it can also form a pair, that is a covalent system in the case, for example, methane. So a covalent bond. So it can form covalent system, can form the negative or the positive bond. So can just see how hydrogen can just be behaving that. Now, in terms of bonding, hydrogen is mostly attracted towards much electronegative element like oxygen, like the halogens, like the nitrogens, and those kind of stuff. So it's a non-metal though, but then it's also attracted towards the non-metal, which are quite electronegative. So that's what leads to what we call the hydrogen bonding. So hydrogen bonding, say for example, in water. Water is oxygen having hydrogen attached to that. Now, if there's another water molecule, the oxygen will be attracted towards one hydrogen, and that is just a weak interaction, just a weak van der Waals interaction. So we can have that linkage all over, and that's how we can be having accumulation of water. So if you see a bubble of water like this, then we have millions of water molecules coming together or being put together by hydrogen bonding, because there's that interactions that we have in that as well. Okay, so talking of this heavy water and that, we can just separate them using fractional distillation. It's quite, but we should say that the pure water is poisonous, so we don't, we don't drink that, but that's what you are calling the pure water. But then the H2O, we drink that. The properties of hydrogen, we see is colorless, is odorless, it's non-poisonous, it's not toxic. Of course, our system is made up of hydrocarbons, so we tend to have more carbon. And in fact, what it means is that we even breathe in more hydrogen than we breathe oxygen. Of course, in terms of weight, hydrogen is lighter than oxygen. So it means that hydrogen gets into our system so quickly and so comes out so quickly, and also aids in some mechanism point at the point in time. If you check the boiling point, very, very light, very, very light. So in the negative, it starts bubbling kind of out. So that's just hydrogen for you. I'll talk about the halides very soon. But then, how do we prepare hydrogen gas? So if you remember we can start from the metal point of view. We can prepare hydrogen gas from there. And of course, in the industry, we prepare hydrogen gas from the fossil fuels, so the hydrocarbons. We can be getting in hydrogen gas from that. So say for example, we add a hydrocarbon to water, then we'll be producing carbon monoxide and then that of hydrogen gas. Or we burn an organic compound or any hydrocarbon or any organic compound. When you burn it in air, of course, we produce carbon dioxide and then the water. Well, that water can also be broken down into hydrogen gas and then the oxygen gas as well. Again, if we have carbon, what you call charcoal, added to water, and of course, with a little heat, we begin producing hydrogen gas as well. Then some soot, which is the carbon monoxide. That the carbon monoxide must be controlled because carbon monoxide is also poisonous. So those cars that releases this incomplete combustion with the smoke following them are really poisoning us. Carbon monoxide stands We're not close to cyanide, but then it's also quite dangerous to our system because of the silt deposit that it can just be. Okay. Again, we can be producing hydrogen gas from water using hydrolysis. When we break down, water will produce hydrogen gas from that. And of course, it's even noted that here from water we can be forming the pure um, hydrogen. That also means that from the atmosphere when we combine, so like the air conditioning combines the oxygen and then the hydrogen to produce water. That water is evolved of kind of ions in that. Of course, the electrolysis process should be quite, it produces almost like 100% pure hydrogen gas, but then it's expensive because you are going to be using power. Now we can also use cracking. So we break down the hydrocarbons and produce a silt carbon and the hydrogen gas as well. That silt, that black carbon we use in printing or where we have this carbon paper. I'm sure you know what carbon paper is.
Yes, sir.
Okay, those if you want to have a copy, like those using receipts and those stuff. If you count now, I think some receipt have the duplicate where when you write it goes direct. If you
Yeah,
still want to see carbon paper, visit the Lotto kiosk.
exactly.
You see carbon paper there. That black kind of it looks like paper stuff, but that's where we use that black carbon that is coming from this cracking of this methane can produce that. We can produce hydrogen gas from ammonia. When we decompose ammonia and at a very high temperature, we are producing nitrogen gas and then hydrogen gas. So again, please note when we get to nitrogen, how to produce that. When we get to carbon, how to produce that. It's almost the same kind of process. Now, for alcohols, we can produce alcohol, hydrogen gas from that. For cooking, that is high water and carbon. I've mentioned that we can produce that. A lot of process, but in a simple experiment in the lab, we can produce hydrogen gas. Yes, yes. I thought I saw. Okay, the person is off. So in a simple lab experiment, once I have say HCl hydrochloric acid, I just drop in a zinc metal. Then I can just get to produce hydrogen gas by just turning that in water. Hydrogen gas is insoluble in water, so the bubbles that I'll be saving out of that water is so this HCl and then there's a zinc there. Well, a little bit shake or just stirring will be just producing the hydrogen gas which bubbles through the water and then can just be saving that. Now in terms of reactions, we can just be getting hydrogen engaging themselves in um, other reactions like say polarization reaction where we form polymers. So for example, hydrogen can form the dihydrogen or what we call hydrogen gas can break down to form um, these radicals. And the radicals can engage themselves with, say, oxygen and produce another radical, the hydroxide radicals. And then it continues until we begin terminating that or that's propagating stage with this. And of course, that process is initiated just using a radiation, a UV light can use that. So it continues and continues till we get to the point where we need to terminate that reaction. I've mentioned hydrogen bonding. Now, in terms of bonding, where we said that hydrogen can be negative, it means that we can have the hydride. We have different forms of hydride. We can have the what we call the ionic hydride or the silane hydride. Then we can have the covalent hydride and then the interstitial hydride or the metallic hydride. Some call it a transition metal hydride. Then, of course, yes, the transition metal, and then we can have, I didn't add it here, but we can have the non-stoichiometric hydride. That has to do with this material chemistry. Okay, but then if I should just take them one after the other. So the covalent hydride is when hydrogen or the hydride that you are forming, of course, it looks negative, but then if you check the bonding, that is purely equivalent bonding that we have there. And these are molecules or the molecular compounds which includes group 6 uh, or the group 7. That's the oxygen related and then the halogen related group. Well, sometimes the group 5 can also be part of it. And these are the covalent systems. So, though, if you are naming it, say, for example, well, this is a common name which you call ammonia. But if I'm naming this compound, this is nitrogen trihydride. And so the hydrogen here is a hydride compound. I'm sure we are aware how we name compounds. That IOPAC gives us ways of naming compounds, whether it's an ionic compound or a molecular compound. For ionic compound, we name the cation, follow it by the anion. So the anion can be a polyanion or a binary anion. So just name the cation or the metal, follow it by the anion part. Now, if the metal is a transition metal, it says that then calculate the oxidation state or the oxidation number for that transition metal, and then put the oxidation state as a Roman numeral between the cation and then the anion. So, for example, we have ion 2, say chloride, or ion 3 oxide. So that's because the ion is a transition metal, we calculate and put it in the Roman numeral. But for covalent compounds or the what you call molecular compounds, we name the first element, or when we are writing, we write the electropositive followed by the electronegative. So we name the electropositive first, then we follow it by the electronegative. By naming molecular compound, we name them by indicating a number of elements that are present. So while if the element is beginning and it is 1, we can ignore that and say it's a mono, but we ignore the mono and just call it there. So for example, this is nitrogen and the hydrogen is 3, so trihydride. Okay, so like water, the common name is water, but if I'm naming it by IOPAC name, this is going to be a dihydrogen oxide. Okay, so the electronegative is what is ending at. So in this case, the hydrogen there becomes the hydride there. And but then if you check the bonding, this is purely equivalent bond systems that exist between that. So like the carbon tetrahydride and those stuff, these are covalent systems that we have in that. So that's, we can just move that. Then we have the silane hydride, which is the ionic hydride. So coming from ionic compound, the ionic in nature, meaning it's an hydride which is combining with a metal. So now it's behaving like the negative one, as a metal behaves like the positive. So that's and it's an ionic compound, like the let's say the lithium hydride. In ionic, we don't name the number of elements there. So calcium hydride. So it's an hydride which exists as in the metallic form. Then we have the interstitial kind of hydride. It's an hydride that is formed between two, like the anion part and then the cation. So it's in between, forming like a bridge, which is in between the two atoms that it's there. But of course, we kind of name just by combining them. The hydride is combined with the anion part of it. That's that. But then because hydrogen is very small in size, and if you compare to like titanium iodide, the size of hydrogen is so small that it can fit into the hole. Assuming the atoms are spherical in forms. When you put them, like putting oranges, it creates a hole in there. And so you can fit hydrogen in there. That is what you call interstatia. It's not substitution, it's just interstatia, which falls in between that. And that's what is called the, so such hydride is the interstatia hydride. Then we have the transition metal. So that you should know that that is coming from transition element combining with that of the hydride in this form. And that some of them can be non-stoichiometric. The ratio of combining them is not like whole numbers. It comes in fractions and those kind of forms. And we see a lot of these in the material chemistry. The ratio, like if I take one oxygen, I need two hydrogen. In a transition, sometimes I can take, say, one, say, yandium, and then I'll take 2.5 of hydrogen. It's not like a pure ratios that you can find in that as well. So we can have that a system there. In terms of the applications of the hydrogen, we'll use hydrogen as in organic reactions, for example, hydrogenation. So we are converting a triple bond, a double bond to a single bond, meaning we just need to push in more hydrogens so that we can break these bonds and then form the single or the straight chain. So hydrogenation basically is just adding hydrogen to a saturated compound, a compound that has a double bond or a triple bond in that. Now, can you tell me the difference between margarine and then butter? What's the difference? Can somebody help me? What's the difference between margarine and butter? So I've said that it's quite important in the production of margarine because we push in the hydrogen gas is sponge where we hydrogenate the alkane to the alkene or sometimes alkane. What's the difference between margarine and then butter? Oh, who is helping us? Oh, so go and buy. So the reason why I'm asking because I've heard people saying go and buy me butter, and what they mean is go and buy margarine. So what's the difference? Nobody will talk. Okay, so butter is from animals, whilst margarine is from plants. So the solid fats that we extract from vegetables is called margarine. Those that we extract from the animal dairies or those dairies, the fats that we extract becomes the the what's the name, butter. Well, so oil is saturated, meaning oil has double bond in there. So if we push the hydrogen in there to reduce the saturation, it becomes hard. It becomes solid. So that's how we have just cooking oil different from margarine, vegetable oil from margarine, or fat oil from butter. That's and the process is just hydrogenation in that kind of form. Again, hydrogen is quite important apart from the hydrogenation. And so we need to find a way of conserving hydrogen just as we conserve oxygen. So we have what we call the hydrogen economy, trying to see how we can be using hydrogen to replace those systems that is taking our oxygen off. So the oxygen-related fuel cells can be replaced by hydrogen, and then we'll recycle that and through that water through the renewable energies, then we can get our hydrogen back. And by that, we can also be saving oxygen also from that. So the recycling of hydrogen is quite important. Well, if you look at some other properties, for solar cell or solar fuels, of course, because hydrogen is odorless, colorless, and lightweight, is that we use a lot of hydrogen or breathe in more hydrogen than we could breathe oxygen. Then, of course, we have other usage of hydrogen. And then what we should be drawing attention to is uh, the use of hydrogen now in the medical field, where they are using hydrogen to treat ulcer and sometimes obesity and cancer. These are the two main, of course, skin diseases is there, but then I know they use hydrogen gas to treat ulcer and then cancer, some form of cancers, and then also because it can change saturation to unsaturation to saturation, so it can help reduce obesity as well. So that's just hydrogen. Now we'll see that I usually ask them to um, try to see if they can describe what we call the hydrogen fuel cell. I have that, but then sorry. So let me write that. So at least as your way of learning and researching, try to see if you can read more on how we can describe this hydrogen um, fuel cells, hydrogen fuels or fuel cell. So that's something which I want you to read about hydrogen fuel cell. It's a type of cell that involves this chemical reaction of hydrogen and oxygen. But then try to see if you can read on that. Who knows? Maybe later you will see it somewhere or find it somewhere. So that's just for hydrogen. Well, as I mentioned, for biological use, we use hydrogen a lot in the enzymes part, in the ATPs, and then ADPs. We have hydrogen playing a major role in the enzyme as well. Again, we'll see other uses of hydrogen in, say, for example, of course, I've mentioned the manufacture of margarine, but then some chemicals, production of some organic chemicals like the alcohols, we see hydrogen at play there. Manufacturing of ammonia using the Haber process. So the Haber process basically is just we having hydrogen gas, hydrogen gas plus nitrogen gas to produce ammonia. This process is called the Haber process. Haber. So that's so the Haber process. Okay. So we know that hydrogen can be used in that forms as well. So I says that. Now we said that hydrogen can form or combine with oxygen to form water, and this water we seen that we can have what we call hard water and then soft water. Can we differentiate between the two, hard water and soft water? Can somebody help us differentiate between hard water and soft? Yes, sir. Yeah.
So hard water does not easily lather with soap, and then soft water
And what
lathers.
what causes that? And what causes that?
So the presence of iron,
The presence of
iron.
iron. Well, I don't get it. Iron. I don't. Which iron? You mean
Okay, the
iron
presence of
as
salt
Fe or iron as this? I don't
iron,
get it.
ions, ion.
Okay. And what ions are you referring to?
So like magnesium,
Uh-huh.
like most of them they are salt.
So
Calcium, iron.
magnesium and then calcium.
Yes, sir.
Yes. Okay. So that causes makes the water difficult to lather. Okay. Now how do we treat hard water? Any process where we can be using it to reduce the hard water?
One is boiling.
One is boiling. Thank you. Any other?
So we can also use ion removers like sodium bicarbonate.
Sodium bicarbonate.
Yeah.
Okay. Any other?
Addition of washing soda or powder.
What do you mean by what is washing soda? What's the formula for washing soda?
Washing soda, washing soda. No, I'm not getting. I've forgotten the formula.
But you know lime soda.
Lime soda, yes, sir.
So what washing
Calcium
soda is
hydroxide.
no
Calcium
washing
hydroxide.
soda is no washing soda is sodium carbonate.
Okay.
And then the lime soda is a calcium hydroxide.
Okay.
Okay. Yeah. So when we add sodium carbonate to that, we can reduce that. Any other? So of course, when we boil through distillation, we can also reduce that soda as well. Okay. I think I want to start the boron, but then we'll give some break and then I can then start
Sir,
another.
hello,
Yes.
sir. I just want to
Yes,
ask
sir.
one on the hydrogen. The hydrogen, how dangerous is hydrogen? Because I was reading some.
Hydrogen gas, you mean?
Yes, hydrogen gas. Yes, because I learned
Uh-huh.
that China is only country who is having a hydrogen bomb.
And that is not hydrogen gas.
Hello.
Yeah, I can hear you.
Okay.
Yeah, so ask your question. I just made a correction from that. And so you ask your question.
Yes, yes. I said that I read that China is the only country who is having the hydrogen bomb, and the way they talked about it is like very dangerous and all those things. That's why I'm asking to find out.
So it's explosive in nature. And that's, it's not dangerous as in having effect in the biological system. It's dangerous because of how it explodes.
Oh, okay.
So each reaction is explosive in nature. So that's where the hydrogen bomb is quite so it's a nuclear kind of reaction. I think I show you here. So in the reaction, let me minimize this. So let me minimize this and then show you the reaction. Yes, this reaction. So it's quite explosive, and then it goes through what you call the nuclear fission.
Mhm.
So unless you stop it, this radical will continue going. So it's
Mhm.
like a fire that does not quench.
Oh, okay.
So once you trigger it using the UV radiation and it explodes with the radical, and then it just goes on, goes on. So it starts with the initiating form. You initiate it, then it begin branching,
Okay.
propagating, going on unless you terminate it. So that's why it's dangerous. It's a nuclear weapon. So the atomic bomb.
Okay.
And I think the World War II, that was what stopped Japan from proceeding. So it
Okay.
stopped, and then up to now, the land of Japan, some part of it have still not recovered to there. An earthquake. It has become an earthquake zone, shaking the land. So it's a hydrogen bomb is a thermonuclear bomb, so powerful that once you initiate it, it begin releasing radical endoscopy. But then the hydrogen gas is not harmful to the system. But the radical, of course, is just reactive, so it just continues going. A fire which you cannot quench.
Okay, thank you.
Okay, so is it 5 minutes or 10 minutes break?
10 minutes.
Okay, so we'll break and then we'll come and continue with the boron.
Are you on break?
Yes.
Okay.
The time is
Okay,
even almost up.
10 minutes is up, so let's resume. If you want to now go for your break, then the break is over, please. So let's continue so that we can finish first. Okay, so now let's look at boron, which is one of the the metalloids. Okay, so we are looking at boron, the group three metals. Normally, the element that begins on the top to bottom is what we use that to call the family of boron. So boron is one of the minerals which, of course, we find them in foods and in our environment, and of course as the earth crust. The all of boron is the borax. I'll show you that, but then we'll kind of see boron a lot in, for example, in avocado pear and this iris soup. They add some boron in that. Of course, boron is used as a food supplement in treating the clamps, like clamp pains, like the menstrual clamp pains. They use that in treating that for the women. The women having discomfort in that, and sometimes the some infections in the vaginal yeast infections. Boron also is used in treating those as well. Now, in terms of making glasses strong, this man we add boron to this sodium calcium oxides and then the silicon oxide to make what you call the borax glasses or the perax, the strong glasses which can survive high kind of temperature. The ore of boron is this borax. So that's a sodium boron oxide, very kind of in that kind of form. Of course, we can also have the orthoboric acid as well. That's also an ore. Then the carnite, that's a more or less like a double of this in the it's also depending on the hydration that we have in that we can have um, the carnite different from the borite. That's how it exists in these forms. Again, for example, when we take borax, dissolve that in acid, we can be producing the boron hydroxide. And this boron hydroxide, when we heat it, can form the boron oxide, which a boron oxide is a reducing agent in this detergent. But of course, when we have a detergent that have this borax in that, it's quite a strong detergent, which causes itching of skin and those kind of stuff. Now, what we know boron is that boron is one of the elements that breaks the what we call the octet rule. Okay, so it creates what we call the incomplete octet rule. It has three electrons at the valence, and that it cannot lose three electrons. It cannot gain three electrons to be six because octet means it's supposed to be eight. So it forms a covalent systems, and that will make boron have an environment which is an incomplete octet. So most of the compounds that boron forms, you see it having an incomplete octet. And so boron itself, just boron can form boron-boron bonds, and then it forms that boron cage and boron cage kind of compounds. But then we can have boron with hydrogen, which we call the borenes. So depending on the number of borane that we have, we can have the diboranes, the triboranes, and those kind of stuff. So if we have two boranes, that is what we call diborane. But it has a general formula similar to that of so like the hydrocarbons. It has also that kind of formula. But boranes are widely studied now, and that we have studied those borings, and we know that they are potential fuels for these rockets and these automotive kind of use. And borings are also good ligands for coordination. It really binds very well. Now, if you look at how the borings are made up of, so you see the borine itself has only 3 valency, but here you can see it has formed like 4 bonds. Now, what we can understand here is that when we take the borine, the bonding in borines, we understand that we can have, say, this borine, where we stand here, we'll have this borine and then this hydrogen. So between the terminal hydrogens borine, we can have just 2 electrons there. And then we can also have 2 electrons here. But then when we stand here and then we are looking at this hydrogen, this hydrogen, this hydrogen, then it means that this borine is going to be having 3 electrons bonding to 3 hydrogen. That is normal. However, it's even more kind of interesting because this borine is engaging this borine in the form of interaction. And then this borine, apart from this, you can see is also interacting with this hydrogen. Now the hydrogen here, you will see has also broken its rule. Hydrogen has only 1 electron. Here it is forming what you call a bridge. So it is just bridging. Actually, it's, if you look at it, it should be like a curve. The hydrogen will just be on top. It's just a bridging hydrogen, which is it. So there's this boron-boron interaction. There is boron hydrogen boron interaction, then there's boron hydrogen interaction. Are we okay? Okay. Now, if I take the boron and then boron interaction, definitely I'm going to be looking at we having 2 centers. That is 1, 2 centers having 2 electrons between them. 2 electrons between 2 centers. Now, if I take this boron, hydrogen, boron, that is going to give us 3 centers. So 1 center, 2 center, 3 centers. But actually between these 3 centers is only 2 electrons which they are sharing. So it's 3 center, 2 electrons. So it's only this boron having this electron. This boron is having this electron with this hydrogen. So this boron is actually not having electron sharing with this hydrogen, but then it's just an interaction which exists between that as well. So we can have, when we take the borines, we can have interactions like the 3 center, 2 electrons interaction like what I just mentioned, boron, hydrogen, boron, or we can have the 2 center, 2 electrons interaction. Like if I take, say, hydrogen and boron, that is just 2 centers, 2 hydrogen. Okay, then the borane or the boron here can also engage another borane. So we can have like 3 center, 2 electrons. And so we can have the closed 3 center, 2 electrons, or the open 2 center, 3 electrons. If I have a borane here, so it's borane, borane, borane. And if it's that third borane here is in a closed system, that is a closed 3 center, 2 electrons. And then we can have, if it is open, we can have the 3 center, 2 electron. I don't know if you follow that as well. Between the terminals, these are just 2 centers, 1, 2 centers, but 2 electrons. That's so the terminal bonding are just 2 centers, 2 electrons. But then in the internal ones, we can have 3 center, 2 electrons, whether if it is borane, that is going to be whether it's a closed borane or just the open boranes as well. So that's what I'm trying to. So I think I should use this one rather to explain. So I thought I was showing that, but that is what I just mentioned. So with the bridge hydrogen there, with 3 center, 2 electrons. With the terminal ones, it's just 2 center, 2 electrons, and then between borane, can have borine, which is two center, two electrons, and then it depends whether the borine is in a closed system or it is just an open system. So that is the borines. Of course, we can predict more shapes of these borines before I come to the preparations of borines and then the reactions of borines. Now, we can, so it means that if the number of borines are just increasing, then we'll be having more cage-like kind of a system. So we use a rule which we call the Watt rule to predict more shapes and then um, I mean how it's going to be forming the cage forms of that. So let me close or let me minimize this and then let me talk about the Waddell's rule. I've given the rules in the distance, so I'll just I mean it's good we practice that. So let me close this and then open that a new one. Okay, so I'm looking at the Watt rule for predicting so the Watt's rule to predict the borings. Okay, now the Watt's rule basically is just giving us step-by-step ways of predicting various forms of borings. And borings, as I gave the formula, can be Bn. So when we have borings, we can be talking of borings in this form BNH N plus 4. So these are the general form. So we have borings. And if these borings have other elements like carbon, then we can have the carbon, the carborings. We can have the heteroborings if we have different elements outside the carbon. We can have sulfur, we can have phosphorus. That's the heteroborines or the zeta salts. The zeta salt is other salts that behaves like the borines. So we can have those salts, also the zeta salts. There's the salt which behaves like the borines. For example, this is a salt B, I mean lead 5 2 minus. This is a salt that behaves like the borings. Okay, so let's try to use the Waddell's rule to predict the structures of these kind of compounds. So I first need to know the formula compound. So if I have the molecular formula for that compound, that will help me predict the structure of that borine. So that's what I'm trying to look at using the Waddell's rule. Very simple. You can know the structure by knowing the molecular formula, of course, just by the number of electrons that we have. Now note that borine is having 5 electrons, and out of the 5, 3 is at the valence electron. I'm sure you are aware. So borine is number 5. Okay, so atomic number 5. So it has 5 electrons, 2 in the core, 3 in the valence electron. Do you agree?
Yes, sir.
Okay, so what it means is that we can have borine forming just as the diborane, I mean the borines which I show you. We can have borines forming 2 bonds, 2 electron bonds. Then, sorry, let me address this. Yes, sir. Send, okay. Okay, okay. Sorry. Please give me just 1 minute.
Okay, sir.
Borine.
Okay. Yes. So we understand that we can have the 2 electron bonds and then the 3 center 2 electron. That's what I said. So we can have two center 2 electron bonds. Then we can have 3 center, but it's just 2 electrons that are being formed. That's the differences in the bonding systems that forms that. But then the various shapes of borine, the various forms of or the various structures which borine forms is in the form of what we call closure. So cluso and then nido. These are the shapes. I'm going to be drawing them for you to see that. Then we have the acnuno shapes. We have the hypo forms. Well, let me just start. So we have borine, borine forms, and then they engage other borine in this form. So 6 of these, so forming this type of cage-like. Okay, so if I should put that, so it forms like a cage, and this is what we call closed. The system is closed. Maybe I should draw it this way, like a triangle, and then forming this peak here and another peak here. So it's quite close. Sorry, it's quite close there. This and also mine with that. So like what shape do we give to that? So there's more like 6 borines at the vertices, and there's nothing missing there. And all of them are binded to the terminal hydrogen. So they have terminal hydrogen. This is what we call close, from the word closo. So it's closed system. So that's where we have close. Now when we lose one borine and it becomes, so this is B6H12. Then the needle will become 5 borines in a cage. Then the needle will become, so the needle is like a nest, needle from nest. Then the needle is like the spider kind of web. So 4 borines. So this is 5 borine. This is 6. This is 4. And it's like a spider web where it's just like that, and then engaging its environment. So 4. Then we have the hypo. Then we have the clodo and those kind of forms. So these are the various forms. So let me list them, and then I'll just give the formula for that. So I have the closo, I have the needle, that's a B5. I have the acno, I have the hypo, then I have the clodo, and then the super closo, and then hyper. Hey, but welcome the one now could know me to my choir. Who is that? Christopher. You from the one I knew that you are an intruder. I definitely knew that this is not your class.
No, I'm part of always. I'm part of you.
Okay, then keep quiet then. Okay.
Okay, sir.
So these are the various structures which I'm just showing. So let me minimize this so that you see. So what I'm showing here is the needle, 5 of them, 1, 2, 5. So if I have one boron here, the system becomes closed, and that is what we call the closed kind of a system. So if I have only 4 here, that is the acno, that's a spider web. So 3, and then that's the triangular, and those forms becomes that form. Now again, so let's proceed. So noting these structures is how the boron forms cages. Now, what we need to know is that we need to have a molecular formula for the boron. Then from that molecular formula, what those rule helps us to predict the structure. And these are the structures that we are going to be predicting. Either it is needle, either it's closo, whether it's acno, and those kind of form. Now, basically, how do we predict that? We know that we have in borines, we have boron and then hydrogen atoms, boron and then hydrogen atoms in that. Now, what we just have to know from or what will help us to understand is that to find the structures, we need to know the number of borines that are there. Then we need to know the number of hydrogens that are there. Then we'll know how many hydrogens that are in excess when the borine excess in the terms of borine hydrogen bond will create excess hydrogen. Then we use a simple kind of formula to just predict that. So how do I know the number of excess hydrogen? Is first to know the number of boron. So let me use N to represent the number of borons in the borines. Okay, so that's the number of boron atoms in the borine. Then M, I'll use M to represent the number of hydrogen hydrogen atoms that are in excess. Sorry, so M will be the number of hydrogen atoms that are in excess. Now I can use this to predict the structure. So the structure which I'm going to be predicting should be N plus the number of hydrogen that is in excess. Okay, so this is how I predict that. Well, normally the N will be fixed for the boron, but then the M is what is going to be changing. Now, when I do the calculation, I notice that I have what's like N for the boron, but then I have 2 excess hydrogen. Then that structure is closo. If I do the calculation, I notice is N plus 4, then that structure is the needle. If I do the calculation and then I get to have N plus 6, that is the acno. If I continue, yes, N
Hello,
plus 8, that is the hypo.
sir.
Yes.
Hello. Sir, please, your line went off, so I didn't hear what you said.
Please confirm. Okay, so I'm just trying to say that we should know the number of boron, then know the number of excess hydrogen that is there.
Yes.
Okay. Now the number of hydrogen should be the same as the number of boron, but then we can have excess of that if we take it out of the number of hydrogen. So I'm going to give you the steps. But then I'm saying that when we do the calculation, this is how we predict the shapes of the borines. When I know the number of borine, but then the excess hydrogen is 2, that is closer. If I know the number of borine, the excess hydrogen is 4, that is needle. 6, that is acno. 8, that is closer. Then 10, N plus 10, that will be the the clodo. Yes. Yeah. Wow, cool. Sorry, you're one of your code people called me. Yes. So yes, so that is the clodo. Now, if I do the calculation, I notice I have N plus 0. That is, there's no excess hydrogen. That is the super closo.
Okay.
Now, if I calculate and then I get n minus 2, that is the hyperclose.
All right.
So please note this. Now, how do I get the number of excess hydrogen? The number of excess hydrogen, which I call M, is equal to the number of hydrogen H minus N. And I know N is a number of
Carbon.
borines.
Boring.
The boron. The boron. The
Yeah.
N is the number of the boron.
Boron,
So
yeah.
how do I do the calculation? The first step that I need to do is to count the number of borons in the borines, which is the N.
Yeah.
So how many boron do I have in borines? That is N. Number 2, then count the number of hydrogen, which is H. Okay. Now,
Yeah.
if the compound contains a charge, for example, it is a negative charge, what it means is that, if it is negative, meaning
It
you
has received
have,
electron.
yes, meaning you have to add you have received electron because there's one hydrogen which is missing. So a negative charge means there is an extra hydrogen to be added.
Okay.
A positive charge means that we should take hydrogen out.
All right.
Okay, so you count the number of hydrogen, count the number of borons, and then check if the compound has a negative charge there. Then how many steps have I given you? 3. So the
Yes.
fourth one is to know the excess hydrogen. How do I know the excess hydrogen? Once I know the number of hydrogens there, and the number of hydrogens, I can count them, including the positive, negative. If it is negative, add 1 hydrogen. If it is negative, take 1 hydrogen. So I can know the number of hydrogen. Then I know the number of borines. I can know the excess hydrogen. Now, once I know the excess hydrogen, I can predict the shape of that compound. Would that be remembered? So let's try one example.
Yes.
Maybe we try more example for you to understand before I can proceed. So, for example, let's take this borine B7H9. Okay, this is a borine. Now, what's the number of borine here? What is N? N is
7.
equal to 7.
7. Yeah.
What's the number of hydrogen?
It's equal to 9.
9.
9.
So what would be the SS hydrogen?
2.
It's got to 9 minus 7.
9
Got
minus
7.
7, which is 2. So if you predict the shape, it's going to be N plus 2.
2. Yes.
And N plus 2 is closer.
Close. Yeah.
So that will have the closer shape. Okay.
Yes, sir.
Let's try one, then I'll give you an example for you to try for me to see. So let's say B10H14. What shape do you think will be? It will be. So N is equal to 10, H is equal to 14, then M is equal to 4. Is that correct?
Yes, sir.
So this is N plus 4, and that is needle.
Yes, sir.
Okay, so try the following. The teacher will always do the cheap one and give you the difficult. So try the following. Let's predict the shapes for the following. Say B2H7 minus. B2H7 minus. What will be the shape?
B2. So, plus 8.
Yes, what's the shape? Yes.
The shape will be B288.
Sorry?
It will be alacloborane.
So that is N plus 6. So that's the Yaraku. So thank you. So you remember that minus means add one hydrogen. So
Yeah,
the
that's
number of
right.
hydrogen is 8.
8. Yeah.
Yeah.
The number of borane is 2, and so the SS will be 6. So
Yeah.
Yeah.
that's N plus 6, and that's
6.
the uh,
Alaklo.
okay. So that's so let's move on to like adding other element to that, like the heteroboranes. Like you are adding, so you can have the carbon or the carb boranes, you can have the heteroboranes or the zeta kind of boranes. Now, if we take the heteroboranes, for example, so meaning we are going to be having other elements like carbon, phosphorus, nitrogen, sulfur, which is added to the borane as well. For example, C2H B C2B 4H6. Oh, C2B4H6. This is a heteroborane because we have so, and this is carboranes. Well, when we have other element attached to the borane, then of course we're going to be following the same kind of counting, but this time we are going to be linking the elements that we have to be like we are counting the borane. So we call it the borane equivalent. Borane equivalent. Now, how is borane going to be equivalent, for example, with carbon? Well, we'll see that borane is going to be having 3 electrons at the valence, whilst carbon is going to be having 4 at the valence. Okay, so if I take, say, for example, carbon, its equivalent to borane will be 1 borane plus 1 hydrogen. That is 4 electrons. Do you agree? So hydrogen has 1 electron, borane has 3
Yeah. Yes, sir.
electrons. So that is 4. Carbon has 4 electrons at the valence. So that is its equivalent. So for example, if I take nitrogen, nitrogen has 5 electrons at the valence. So its equivalent will be 1 borane, 2 hydrogens. If I take oxygen, oxygen has 6 electrons at the valency. So can you tell me its borane equivalent? That will be BH3. 1 borane, 3 hydrogens. That's a borane equivalent. So what we can draw here is that, or the conclusion we can draw here is that when I take the boron kind of group, so boron, aluminium, gallium, indium, thallium, they are in the boron group. Okay, so they are equivalent to borane. So once you see them close or in a borane kind of structure of compound, then they are equivalent to borane. So the borane group, that's aluminium, gallium, indium, thallium, they are all going to have the boron equivalent. But when I move to the carbon group, the carbon group is carbon, silicon, help me, germanium, tin, and then lead. They are all in the carbon group. So they are equivalent to be having 1 borane and then hydrogen. Now, if I take the nitrogen group, which is
Hello, sir.
nitrogen, yes,
The in terms of carbon, the combination is, are we using the charges or we are using the number of valence electrons?
the valence electron. So
Okay.
boron has 3 valence electron, carbon has 4 valence electron. So it means that when I take 3 out of 4, I'm left with 1 electron. So hydrogen has 1 electron at the valence, so I can have that equivalent.
Yeah.
Is that okay?
Yeah.
Are you okay?
Yes, please.
Okay. So I'm talking of the nitrogen group. Can you help me? That's nitrogen, phosphorus, is it the arsenic or the uh, tin, and then the bismuth. So they are going to be having borine equivalent of BH2. Then the oxygen group is oxygen, sulfur, selenium, and then this titanium, and then the polonium. They are going to be having equivalent of BH3. Now again, note that we can't have BH4. Boron cannot take more than 3 hydrogen. So the equivalent will just end with so we can't go to the halogens and say that the halogens should have boron equivalent of 3 and those kind of. But then when it comes that we have halogen, but borines don't have halogen, but then if it has, then we can say that we should have 2 of the boron plus 1 of the hydrogen. That is 7.
Yes.
Okay. Now, once we know the equivalent, then we're going to be converting this element which is combining with the borine we use the equivalent to represent that element so that we can now count the number of borine total. So for example, when we take carbon here, the carbon equivalent for borine is BH. So it means that in this case, we are going to be having BH, but there's 2 of them combining with B4 and H6. So total, we're going to have B2, H2, B4, H6. So total of B6, H8. Is that correct?
Yes, sir.
So now we can quickly predict what the shape will be. So the N is 6, the H is 8, and so the M is going to be 2. So such as from a shape will be the closure N plus 2. So that's the hetero atoms. Can we predict more? So let me give you another example that you try. Okay. So let's try this and predict the shape for me. How about SB9H11? Can we predict what that shape will be like? Uh, yes, if you finish, we try so that's number 1. Number 1. Number 2, predict MESI to metal silicon boron 10H10. What is the shape?
No, how to go back?
Number 3, C2B7H11. Okay, let's do just do this 3 and then we move on to the zeta salts. Uh-huh. Any answers? Oh, or you are waiting for answers. Christopher, who did you?
What you say?
Who did he?
Galivina na maybe book.
And where we are there for one, they know my answers.
Tell me
Yeah,
go so
so
much me go so.
as I should still wait.
But I was not here, so I did not hear it well.
Oh, oh, okay. Yeah,
I
so
sent
let's
someone
take
to go.
the first. Let's take
Well,
the
I
first
think
one.
the first one will be Nido.
Which one? They yes, you are
The
correct.
first one.
Yes, you are correct. That's a n+4, eh? So sulfur is in the oxygen group. So sulfur, the equivalent for sulfur will be BH3. Is that correct? So if I add it to that, I'm going to be having B10H14. So meaning the M there is going to be 4, and that is the n+4. That's needle. How about the second one? That's the second one. But the second one, the methyl group here is a substituent. It's not so our focus is just going to be the silicon, which is 2, then the boron, which is 10, hydrogen, which is 10. Now, silicon belongs to the, tell me which group was that? Silicon is in the
Carbon
uh,
group.
carbon group. So what's the equivalent for that? Carbon group
BH.
BH, and we have 2 of that. So that is going to be
B2H.
B2H2. So
Yeah.
when we combine, that is going to be B12H12.
Yes.
So there's no M is going to be 0.
0. Yes.
And when N+0 is going to give us what shape?
Super close.
Super close.
Yeah.
Okay. What's the last one? Maybe that's why you do that. I think the last one we did that. Or it was not. So this will give us a needle. Please confirm for us. Let's see if that is correct.
H2.
Okay. Now let's look at the acetyl salt. Let me close this. Acetyl salt, which is
Yeah,
okay.
they're doing
So that's the acetyl salt. We are looking at the salt that behaves like the borings. They are actually not borings, but they behave like the borings. So when we are predicting their shapes, we use the Waddell's rule in trying to predict the borings to just predict that. Now, say for example, we have say SN 92 plus. Okay, or 4. The correct way is 4 minus, not plus. Again, we understand that in the borings when we're counting, when it is a charge, negative charge means we'll add 1 hydrogen. Positive charge means that we'll take 1 hydrogen from that. Okay, so we'll look at the borane equivalents of these elements there. Then we'll count the number of boranes, count the number of hydrogen, then see the excess of this hydrogen. Then we can predict the form. So, for example, SN9 4 minus, SN9 4 minus. I mean, you remember SN will belong to the carbon group. So what it means is that the borane equivalent will be BH. So in this case, we're going to have BH9 4 minus. So that is going to be B9 H9 4 minus. So N is equal to 9. H is going to be how many?
13.
13. So N is going to be
4.
4. So that is N plus 4. And N plus 4 is what?
Needle.
Needle. Okay. You want more example, or we can just end it there and then?
More example. More example.
Oh, okay. So let do for what is it? Say okay, let's try. Can you try this? S4 2 plus. S4 2 plus PB5 2 minus. PB5 2 minus. Yes.
But your size, how much you different? 4 by 8, then 5 by 8. Which one you want? What's number else? So that's 2. Yeah, which guy? 5 by 8. One fine. I put 162 number 2, 3 2. Now 4 by 8 now which size? And then 1 2 8. So you can go 2 5 6. Every
Yes. What's the answer?
S4 is hyper. Is it
Yes,
hyper?
S4 is not. Please,
it's
a
hyper,
different
yeah.
answer. Oh, where's my pen? Yes, you said it's what?
It's hyper close. S4.
S belong to the oxygen group. Is that
Yeah.
correct?
Yes, sir.
And that the oxygen group is
BH3.
B3,
Yes.
and that we have 4 of that. So this is B4, H12, and then plus 2. So N is equal to 4. H is equal to what?
12.
This is plus. H is equal to
10.
10. So
Yes.
then it's M is equal to 6. So that is N plus 6. And N plus 6 is not uh so N plus 6 is what? So the N plus 6 is the acno.
Yes, that no. Yeah.
Okay. How about the
I know what
PB5
to
2
say.
minus? PB5 2 minus.
PB5, so the same thing.
So that's the PB. Lead belongs to the carbon group. So carbon will have BH, and we have 5 of that. So that is B5, H5, 2 minus.
Yeah.
So N is equal to 5, H is equal to 7. Be agreed.
Yes, sir.
So N is equal to 2. So it's N plus 2, which is closer.
Yeah.
Okay. Well, so I've gone through that with you. So the rules are just there. But let me just make a summary of that. So from from literature, this is what we are looking at now. The shape, the closure means that there's no, all the vertices are complete. If you take the needle, if you want to draw it, you see that one vertex is missing. Yeah, acno is two vertices missing, the hypo is missing. In literature, we have structures solved for the closure, structures solved for the needle, the acno, the hypo, but there's no real structures, real molecules solved for the clodo and then the superclodo and that of the hypocloso. There's no quite any structure which is formed, solved. But in theory, we can just proceed using just that to predict the various kind of shape that we have. So I've put here those, if you, maybe I was rushing, if you also want to learn more, you can get to have the video from YouTube and then you watch it. I have the video here, but I think this is clear enough if you want to understand. I don't need to play more to just understand. So this is how it looks like. So this is the coming from the trigonal. So this is a close, so the tetrahedron forms all having close. So we can have more electron counting and then more kind of predicted from. So from closer to the needle, one vertex is missing. So depending on the boring that we have, we can have a lot of shapes that we can predict from that. Now let's look at the
No, sir. Sir.
yes.
So even if one vertex is missing, it means it's assuming the same name. The name does not change.
No, when the vertex is missing, it changes to a different shape. So when it was close, so one vertex is missing, it becomes a needle. When it is needle, one vertex is missing, it becomes acno, and those kind of form.
Okay.
Okay. So that is just that. Now we can just prepare the borings both from the industrial forms or the laboratory kind of form. In the industrial, they use the boron fluoride. Please again try to help me correct this. Where's my case? Or let me correct it and then bring it back. So it's B3, FE3. Let me correct and bring it back, otherwise I'll forget it. So that is 3 underscore 3. Okay. Yeah, so we have the boron fluoride mixed with the sodium hydride to produce the diborate. In the laboratory, once I have sodium borate mixed with iodine, I can be producing the diborates. And as I mentioned, the diborates or the borates are used as fuel for rockets. Okay, so firing rockets. And so the demonstration of that, if you have a sodium borate, react or add iodine, that you begin generating this gas, which you can use for these rockets. Or if forms, you can also try to see if you can freeze it and get it in a powder form to design your own rockets that can fly with these fireworks and of stuff. It's a nice gas which has a very low boiling point, very flammable. So you just eject and then go high. Now for reactions of these the borings. The borings can react with oxygen to form the boron oxide. It can react with, so let me minimize again and write, sorry. And it can react with, okay, let me close this. So we see that the borings, say for example, the common borane which we normally have is the diborane. So the B2H6 can react with oxygen to produce the the boron oxide. Okay, while water will be evolved out of it. Then we can have the diborane reacting with water, maybe 6 moles, to produce the boron hydroxide. The boron hydroxide, this is 3. And then hydrogen gas is also going to be evolved. And this reaction is quite instantaneous. Once you have the diborane react with water, then it just explodes with the hydrogen gas from that. Now the diboranes, so the diboranes can also react with alcohols. Any of the alcohols, we can be producing the boron aquoxy. So the boron aquoxy, boron aquoxy. This is, and of course, again, hydrogen gas will be evolved. Then we have the diboranes reacting with an acid. Then we're going to be producing the borine hydride, so 2,5-Cl. The borine hydride, hydrogen gas again will be evolved. Then borine reacting with the halides, that again will be producing the boron hydride, for example, the boron chloride as well. So these are the reactions of these borine. Again, we can see it can react with metals like sodium. So borine, diborane reacting with that will form the sodium borate. So sodium borate. And of course, sodium borate, if you add the iodine to that, you can prepare the diboranes again. So sodium borate, and that sodium borate can also react with the diboranes. And the reaction try to continue as well. Well, again, when I get here, I also tell you that try to see how you can really help me understand the bonding system. For example, in diboranes, try to explain the bonding system between this 3 center, 2 electrons. But then when we take, say, ammonia, when you take ammonia has 3 center, 3 electron. So try to help me understand, this type of bonding that exists between the bridging. I'm trying to even answer myself. So explain why the BHB bond is not the same as the NHN bonding. Let's try to help me explain these two bonds. This is N. Explain why BHB bond is not the same as NHN bonds. So try to help me understand. Later, maybe we never know. So try to help me understand that as well. Okay, so that's the borings. Of course, we can have other compounds like the boron hydride. Let me minimize this. Or okay, let me just try to see if I can. So the boron hydrides are also available. Then we can mean boron hydride, meaning boron with the hydrogen as the negative form. So we can have the boron hydride there. Then we can have the boron halides also available. I think the boron hydride, we've seen that example is the borines. Then we can have the boron oxides, like the acid, orthoboric acid. Okay, so that we can also get to have different borane there. Well, let me try to see the uses of borane. I've mentioned that borane somehow it helps in treating these clamps and those stuff. We use borane in the form of the borax for water treatment. That classifies or clears the, for example, swimming pool or say some aquarium, makes it quite clear. and we use boron also in some kind of detergents. In medicine, we have boron, which helps to prevent osteoporosis, and that it helps in treating these bones that are fragile in that kind of form. So we'll get to have that. We use boron in glass, which makes the glass so strong, which we call the Paris glass. I think um, those very strong glasses, which we use in the lab for heating some stuff, the borax glasses. Well, in alloys, we see borons there. But then, as I mentioned, one common example of the oil of boron is the boric acid. So we have the parent name is the orthoboric. Then as we are losing the oxygen or gaining, adding more oxygen, we can have what you call the metaboric or the boric. So boric acid is the same as the orthoboric acid. That's a parent name. Then as we add on other take oxygen or add on, we can have the tetraboric or the metaboric kind of acid. So please know that I've just gone through the use. For the health benefits, we have a lot health benefit for boron, for our bones, for arthritis, and those kind of a lot of health benefits. Of course, where we can find sources of these boron, which is healthy for us, is when we can get some from beans, nuts, wholesome gray, avocado, those boron supplements, berries, plums, oranges, or grapes. We can have these boron, which is quite a supplement for us. It's really good binder for calcium. So it goes with calcium and try to help strengthen that. Okay. So I want to pause here. The next time we meet, we're going to expand more on the carbon chemistry. Very big. Of course, we can't deal with all of that because it's even a whole field on its own, which we call organic chemistry. So, but we'll take the inorganic chemistry out of it. So next Friday, we'll look at the carbon chemistry. So please, any question? Okay. So see you on Friday at is it 6 p.m. Yes.
Hello, sir.
Yes, sir.
So please, last week I sent you the message, but the past questions and those, we didn't get it.
Ah, really?
Yes,
Who
sir.
has been? And then you don't have my WhatsApp. There's this guy. I didn't save the number, but I sent it to one guy. I don't know even before starting the class. There is this guy who uses Eagle as his profile picture. Who is that?
So please, I'm here.
Please, why didn't you send it? Yes.
Please, I have sent it. I posted it in the group.
Okay.
Main chemistry.
I placed it.
The tutorial question is on online main
It
group.
is moving online. Yes.
Okay. So please, if you have a group, share it. I don't know. So maybe I told you. I mean, if you are using my Ghana number to contact me on WhatsApp, that is not going to go through. I to go through, but that is not me. I'm not the one using that number for WhatsApp.
Oh, okay.
So I have a foreign number, and this person contacts me for those things. So I've shared this long time.
Okay.
I've even shared a complete note online for them.
All right. Okay.
Okay.
Thank you.
Okay. So see you on Friday.
All right.
Sir,
Yes, sir. Yes, sir.
I beg you. What about the carbon chemistry? We have not gotten that right yet.
Oh, that's what I'm saying. So initially, I sent the up to the boron, but then
okay.
I've sent the complete notes up to the.
Yeah, we want the
I've sent the complete note up to the halogens. I mean the noble element, including tutorial questions. So if I don't know if you have a platform, I can share everything
Yeah,
I can.
that's the online.
Ato can take it
So
and give it to us.
I'm not on your online something, so I don't know
No,
whether.
Okay.
I don't have his foreign number. So the one that I sent a message to, it
So
didn't go through. So
so
Bright should do that.
Ato, let's do
Okay.
it this
The
way.
one that is having the number should do so with the bag.
Yes, yes.
Wait, Ato, so you call me, I will send you a hi using my WhatsApp, then we can take it from there.
Well, so please, I should call you on the Ghana number.
Yes, the Ghana number is for only calling, not for WhatsApp. So you
Okay.
call it, then I'll save your number, and then
All right.
I'll send you a hi using my WhatsApp.
Okay. Thank you.
Okay. So see you on Friday.
Yes,
Okay.
sir.
Okay. Thank you, sir.
Okay, guys, let's look at this question that he said. He said, why is it that the BHB, that's the boron hydrogen boron, is not the same as the nitrogen hydrogen nitrogen?
Yo, Mr. Eagle, Bright. Bright.
Yes,
Yo,
sir.
Bright. I
Yes,
beg,
sir.
what's up? What's up?
Cool. Cool.
I beg, give me the stuff there. I do a push give me.
Yeah. Got it.
Okay. The group I created, it seems
You see?
okay. Then I have to paste it in the main group.
I know the chemistry group.
Why?
So the
We
chemistry.
have created a platform for only the main chemistry for
We
online.
are two of us are there.
I'm not
Uh,
on it. That's why I did not receive it.
So
maybe
give
that's
your
fine.
number. Who is the
Yeah.
admin?
I'm the admin.
So taking number then admin.
Okay, then okay, I'm writing your number.
Why?
I say, Ato, phone number
Yes.
then.
Hello, 02408
02408. Okay.
20008.
0008. Okay. Okay. Then I'll add you to the group. 02408
08 2.
0008.
Yes.
Okay. Thank you. I'll add you.
Fimpon. Fimpon. Hello, Fimpon.
Yes.
I beg you. After
Bimpon.
that, you not to that. My dog can add to that.
Mpacha, I'm there two group in it. Or this enemy and I'm this answer to post to two group in it.
And yes, safety chemical laboratory now the toso.
Main way no. The question is not the same name, you know. I answer with red ink.
Safety no word on the same thing I use word.
Message so they are to me.
And a main group in that. Okay, me here. And the pass answer back to the bill. And that's how Jimmy number 9 shall say, Bia, Miss Free to
Okay, the family. Send me maybe on the back.
0243
0243.
021
Okay.
433.
433.
0243.
0243 433.
Yeah, I'll be Edward.
Mpacho, you okay?
Okay.
Yes.
Say cash.
Hey, cash. A bank on credit ate. Was it? Cash is on brody mo no. Cash and two count.
Yente. Ya wonsa wo si body bi ase wo ho baby.
Bonum brody. Cash and two count.
David. Mem kwa de mente.
What's it? Senior man, hello, man.
Yeah, but you know, question I know come as NHN, you know. It's more about electrostatic attraction and weaker interactions. Whereas
Okay.
BHB is about the localized electrons and covalent bonding.
Oh, okay.
Hello, can you hear me now?
Yeah, Cash,
Yeah, I
can
can
hear
hear
you.
you. Yeah, we can hear you.
Please kindly take my number and add me.
From point, the Cash in the number no.
Please, without you, I can't make it to.
Bubo number.
0249
0249.
17
Okay, Pastor.
11
11.
86.
6. Okay.
I come.
0249. Okay.
Hello?
Yes.
May I go over?
Yes,
Watch
please.
the
Okay. As
Okay,
0249
Mature. Okay, no.
17
Okay.
11
86.
86.
Yes.
Yo,
But
don't worry.
I come.
I will bring you people plantain, the fried one.
Hello.
Can you hear me?
Love with me.
Okay, black
Yo,
That's
so right.
055
8
8.
200
Okay.
195.
195. Okay.
Yeah, no.
Guys, we'll talk. Eh?
Okay.
Masano invitation. No, meet me. I don't. That's some invitation.
Myself.
I was referring to Bodato.
Okay, then later.
Okay.
I thought
Yo, bye.
Okay, I'm joining.
Yeah, it didn't work out.
Oh, okay. Oh, not just I come home.